everyone, in this video we are going to be talking about how to draw Lewis dot diagrams. So Lewis dot diagrams is one of the three ways that you can represent atoms. The other two are for Rutherford models. And these models have the nucleus in all of our shells. For instance, if I was drawing the Bohr-Rutherford model for carbon, I would have my number of protons in the nucleus. I would have my shells, and then I would have my electrons spread out on those shells, with the first shell holding a maximum of 2 electrons, and the second shell and third shells having 8 electrons, and the last shell having 2 because we stopped drawing at calcium. So Bohr-Rutherford models is another way that we can represent our elements. So this is a Bohr-Rutherford model, and our most basic Dalton models, where our elements are just represented as circles. So if I was representing a Dalton model of carbon, it would just be a circle with the element symbol on the inside. So what we're going to be talking about is the third commonly way where we represent Lewis dot diagrams, and this diagram contains 2 key pieces of information: our element symbols and our valence electrons. But what we're going to do is we're going to recap where we would find that information. So if we look at our trusty periodic table, there's 2 key things that we need to remember. We need to remember our group number, and our group number tells us the number of valence electrons. And again, valence electrons are our electrons on the last shell. And we know this because our groups are the columns. So if I'm looking at my periodic table, group number 1 would be our first column. It all has 1 valence electron. Group number 2 would be our second column with 2 valence electrons. Group 3 with 3 valence electrons. Group 4 with 4 valence electrons. Group 5 with 5 valence electrons. Group 6 with 6 valence electrons. Group 7 with 7 valence electrons. And group 8 with 8 valence electrons, and helium being our exception. But we'll talk about helium a little bit later. So the key thing that I need to remember is that my groups represent my number of valence electrons, and my valence electrons are the electrons on our last shell. The other key information that we actually get from our periodic table is our period number, and that actually tells us the number of shells. So if we're looking at our periods, my first row would be period 1, so I'd have 1 shell. My second row would be period 2, so I would have 2 shells. My third row would be period 3, so I have 3 shells. Fourth would be my fourth row, so 4 shells, 5, 6, and 7. Now, when we're talking about Lewis dot diagrams, our key information is that we need to know our group number, because in Lewis dot diagrams, I'm only recording 2 pieces of information. I'm representing the element by using the element symbol, and I'm representing the number of valence electrons by its group number. My period number, it's important information, but I don't need it for Lewis dot diagrams. I would use this for Bohr-Rutherford models. So to figure this out, just like as I said, for Lewis dot diagrams, we need 2 pieces of information. Our first being our chemical symbol, which is the 1 or 2 letter symbol that we have on our periodic table. And our second is our group number, so the number of valence electrons. So what we're going to do is we're going to do some practice on our drawing Lewis dot diagrams. So if I were to look at something in group 1, so for instance, hydrogen. So hydrogen is in group 1, period 1. So to draw the Lewis dot diagram of hydrogen, I would draw the chemical symbol, which is hydrogen. And because hydrogen is in one group, group 1, it would have 1 valence electron, so 1 dot right there. If I'm looking at something in group 2, so beryllium would have the symbol Be, and because it's in group 2, it would have 2 valence electrons. Now when I'm doing Lewis dot diagrams, I need to actually position my dots in my cardinal positions first. So it would be north, then east, then south, then west. Once I filled up my cardinal positions, then I can start buddying up. So anything in group 2, so beryllium would have 1 electron here, and then my next electron would be in the next position. If I look at something like boron, which is in group 3, my element symbol, 1, 2, 3 electrons. If I look at something like carbon, which is in group 4, my element symbol, 1, 2, 3, 4 electrons. So anything in group 1 would have the same number of electron configurations. So hydrogen would be in group 1. Something like lithium. Lithium is in group 1, so it would have 1 valence electron. Sodium, group 1, 1 valence electron. Potassium, group 1, 1 valence electron. Everything in group 2 would have 2 valence electrons. So if I'm looking at everything in the second column, so this would include beryllium, this would include magnesium, calcium, strontium. And what would happen is I would have my 2 electrons, first in my north position, second in my east position, and so on and so forth. So that means everything in group 3. So I have boron, I also have aluminum, I have gallium. I would have 1, 2, 3 valence electrons, 1, 2, 3 valence electrons. So same thing, everything in the same column have the same number of valence electrons. Once I get to something like in group 5, so if I'm looking at nitrogen, I have my 4 in my cardinal positions, and then I start buddying up. So something like nitrogen would have 1 in the north position, east, south, west, and then start buddying up. Same thing like phosphorus, which is right underneath nitrogen, 1, 2, 3, 4, and then the 5th buddying up. So this would be group 5. Something like group 6. So for instance, oxygen, I would have 1, 2, 3, 4, and then buddy up 5 and 6. Same thing if I was looking at sulfur, 1, 2, 3, 4, 5, 6. So this would be things that would be in group 6. Just going to erase this because it's in the way. Something like group 7. So let's choose bromine. So a little bit further down, group 7, I would have 7 dots. 1, 2, 3, 4, 5, 6, 7. And again, each of these dots are the number of valence electrons. If they're in the same group, they have the same number of electrons on their last shell. Now, group 8 is special because group 8 has all of their spots completely filled. And that's what makes group 8 a very particular group, that they don't form molecules because all of their electrons on their valence shells are occupied. So if I'm looking at something like argon is in group 8, so it actually would have 8 valence electrons. Same thing with something like krypton, which is also in group 8, would have 8 valence electrons. There is an exception, and this is an extremely important exception, is helium. Helium is the only exception to these rules because helium, even though it's on top of group 8, it only has 2 valence electrons because helium, if we remember, on our first shell, it can only hold a maximum of 2 electrons. And it's actually full at 2 electrons. So helium is the only Lewis dot diagram where it's He, and both dots are actually buddied up, one on top of each other. And this is to show that the shell is full. And this is actually not true with anything else in group 2 because there's actually more space in our valence shell. So moral of the story for our Lewis dot diagrams, we actually have 2 pieces of information here. Our element symbol, which we find on our periodic table, and our valence electron, which is again our group number. So everything in the same group, so if they're in the same column, it has the same number of valence electrons. And how we do it is we place the electrons in our cardinal position first, and then we buddy them up. So that means everything in groups 1, 2, 3, and 4, they are single. And then when I get to group 5, all the way to group 8, that's when I start buddying up my electrons. And my exception is helium, because I draw helium as 2 electrons buddied up right away. So I hope this helps and that you have a great day.